All right, guys, welcome to your online lesson for today. First things first, this first example I'm actually going to have you guys do on your own. So go ahead and put these numbers into your L1 and L2, and please answer the question. Please note it says to calculate and interpret the mean and standard deviation of x, where x, remember, that's going to be your number of units that a person is taking. So go ahead and pause the video and complete that example. I will be here when you guys get back. All right, hopefully you've done that. Remember the amount of work that you are supposed to show here. I asked you guys to write out the first two terms, ... and the last term before you give the answer. The first part is going to be the mean. So most of you guys probably did this okay on the calculator. So you want to show the first two terms, ... and then the last term, and you get 14.65. Don't forget your context. This is going to be units. Now, the part that a lot of people forget is the interpretation part. So if you said something like, on average, full-time fall semester students take 14.65 units in the fall semester, something like that, that would be correct. The second part is going to be the standard deviation of x. Hopefully you guys used your formula sheet and not, your notes. Again, get used to using your formula sheet and interpreting what's on your formula sheet, because that's what you're going to have. And you probably wrote out something like this. If this is what you wrote, it is incorrect, because this is actually the formula for variance. If you want to do standard deviation, you actually need to remember to do the square root of all of those things. So if you don't have the square root, it's incorrect. So be careful of that. That's something very often that students get wrong on the quiz. Of course, your answer, most of you guys probably got that part, is 2.06 units. So for your interpretation of that, if you did something like the number of units a full-time student takes differs from the mean by 2.06 units on average, something like that, that would be a correct interpretation. Now, it turns out this is a distribution for the number of units that they take, but each credit hour, each unit, costs $50. So if I define a different random variable and let t represent the tuition charge for a randomly selected full-time student, there is a relationship between the number of units someone is taking and the tuition that someone is charged. So in this case, I can define the variable t as 50 times the entire distribution of x. Now be careful here, because these capital letters represent an entire distribution, not just one value. This is really, really important, and it's actually critical for the next part of this chapter, which, as I told you guys in class, is the most difficult part of this chapter. So I'm doing 50 times this entire distribution. So go ahead and put these numbers into your L1 and L2 and calculate the mean and standard deviation. You don't need to interpret this time, just calculate the mean and standard deviation, and I'll be here when you guys get back. Okay, hopefully you wrote down something like this. Don't forget to show your work, don't forget your units. And for your standard deviation, again, probably there's still some of you guys that are doing this. Don't forget you have to put in that square root sign. If you don't do the square root of that whole thing, you don't actually have work for standard deviation. Remember, if your work is incorrect, your answer is wrong. And you probably got an answer for that as well. Notice the units, this is in dollars because we were talking about the tuition charge. Now, there seems to be a relationship between the mean for the number of units, this number over here, and the amount of tuition. In fact, this mean times $50, or $50 per credit hour, is this number here. And the standard deviation as well. If I take the standard deviation of the number of units and multiply that by $50, I end up with $102.80. So it seems if I take a random variable and I transform it by multiplying the entire distribution of that variable by a constant, the same change is going to apply to the mean and standard deviation. I can get the mean and standard deviation from one by using the mean and standard deviation of the other. Oh, whoops, sorry, that should be an x there. Should have been an x there. I should be able to calculate those directly one from the other without having to do it. But let's say we have something slightly different. Let's say that in addition to tuition charges, you have to pay student fees of $100, and this is pretty cheap. So it's going to be $100 plus $50 for every credit that you're going to be taking. So if I define another variable c to be overall cost, then I can calculate the overall cost by taking the distribution for the number of credits, multiply that by 50, and I'm going to add this constant 100 to it. I would get a distribution like this. If I put these numbers into my calculator and calculate the mean and standard deviation, the mean, it turns out, is $832.50. Now, wait a second, and see, does that match what I figured? I mean, if I add 100 to this entire distribution, which this is t, which is this one over here, what I'm doing is I'm taking the distribution of t and I'm just shifting the entire thing. I'm not changing units this time, I'm just shifting the entire distribution to the right. So it makes sense that the mean is going to be shifted 100 units to the right as well. So I expect to get that. That kind of makes sense. And again, if I do that for the standard deviation, I put these in my calculator and I calculate the standard deviation, I'm going to get that the standard deviation of the total cost is going to be $102.80. And this actually makes total sense. What I did is I took this distribution here and shifted it to the right by 100 units. It did not increase in variability. It did not decrease in variability. It's not becoming more or less variable. So it makes sense that the standard deviation is not going to change. So the mean, I can calculate this way. If I know what x is, I can calculate that directly. The standard deviation, though, that's just going to be multiplied by the adding or subtracting does not affect it at all. And this should look familiar because in Chapter 2, we looked at the effects of transformations on shape, center, and spread. Remember, if you multiply or divide each observation by some constant, so you multiply or divide, that's going to multiply or divide your measures of center and location. It's going to multiply or divide measures of spread. It doesn't change the shape. So hang on a second, what do I mean by measures of center and location? Well, I'm going to mean things like mean, median, quartiles, percentiles. These are measures of location, things like that. Your max, your min, stuff like this. Measures of spread include things like standard deviation, range, interquartile range, stuff like that. So multiplying or dividing changes your measure of center, changes your measure of spread, does not change your shape. Now, if I transform a distribution by adding or subtracting a constant, again, that would add a number that would change measure center and location, but remember, it doesn't change your spread because all you're doing is you're shifting the entire distribution to the left or to the right. It doesn't stretch or shrink it. It doesn't become more or less variable. Things are not going to be further away from the mean. Things are not going to be closer to the mean. They're just moving over. And also, it does not change the shape. So if you need to go back and review Chapter 2, some of you guys could probably stand to go back and review that anyway. This is going to be really, really important as we move forward with Chapter 6, especially the material that we're going to go over next class. Because again, the material we go over next class typically is the hardest part of this chapter for most students. Now, don't forget, we're transforming these distributions, and we're going to be doing these linear transformations of these entire distributions. This is really important here. You're not transforming a value of a variable. You are transforming the entire distribution. So remember what happens. If I take some distribution x, I multiply it by a constant and add a constant, that is going to change a few things. So if I'm multiplying and I'm adding, first of all, it's not going to change the shape. It's going to have the exact same shape because multiplying, dividing, this stuff, none of this changes the shape. That's going to be exactly the same. The mean is going to change. Both the multiplication part and the addition part is going to affect the mean. The spread, though, for instance, this measure of standard deviation, measure of spread would be standard deviation. It's only the multiplication part is going to affect it. The adding or subtracting does not change that at all. Just a caveat here, just remember, add, multiply, or divide first, then add or subtract. That's your order of operations. You might have learned it as GEMDOS or PEMDOS, something like that. Just don't forget to do order of operations. All right, here's a simple example. Here we have a carnival game that involves tossing a ball into numbered baskets. So you can put these numbers into your L1 and L2 if you like, but I've already gone ahead and given you those answers. So if I throw the ball, these are the possible values. Again, this is your probability distribution, so it's all the possible values, or all your possible outcomes. So you could get 0, 1, 2, or 3. And the probability of each of these outcomes, 0.3, 0.4, 0.2, and 0.1. You can go ahead and put those into your calculator if you want and make a histogram. I mean, I'm going to ask you about the shape of this distribution. But I did give you the expected value of x. Remember, expected value is the same thing as the mean. And standard deviation, obviously, is just going to be the standard deviation. Now, suppose that it costs $2 to play every time you play for every ball that you toss, and you're going to earn $1.50 for every point that you earn. So if you throw it and land in a basket that's 2, you're going to earn $3. Because if I get 2 points times $1.50, that's going to be $3. Now, I'm going to define a variable y to be the amount of profit. So the amount of profit I make So for instance, for this example, I said it's 2. So if I got 2, I would earn $3 minus the $2 I had to pay in the first place. So let's think about this. How can I define y in terms of x? So if I take x and multiply by $1.50 and then subtract 2, I would end up with a distribution of y. So I have a distribution of x. What I can do is I can define y in terms of x by saying, all right, I'm going to take this distribution of x, I'm going to multiply all its values by $1.50, and I'm going to subtract 2, so I'm going to shift that entire distribution over. So now hopefully you have this distribution of this variable in your head. I would like you guys to go ahead and describe for me the shape, center, and spread. So pause the video now and go ahead and complete that. I'll be here when you get back. So hopefully for your shape, you were able to figure out this is going to be slightly skewed to the right. I mean, you can just make a quick and dirty histogram and see, okay, there's going to be some skew there. The center. Hopefully you wrote out some work on your paper, something like this, your expected value of y. You can calculate using the expected value of x. Of course, I want you to do this in context. So in context, hopefully you said something like, in the long run, we would expect to lose 35 cents each time you play the game on average. For the spread, what would I expect to happen? So hopefully you showed me some calculations, maybe something like this. And for the interpretation of this, describing this in context, you'd say something like, on average, you'd expect your profit to vary by around $1.42, around a loss of 35 cents. Because again, that's the mean. This is going to be the average distance from the mean. So this is the average amount I expect to vary by from this mean of negative 35 cents. All right, the last example I would like you guys to do on your own is the next one. So this one, actually, I would like you guys to see if you can do this on your own. So pause the video here and complete this example. I will be here when you get back. Okay, hopefully you didn't have any trouble understanding this question. So in a large statistics class, we have a distribution of raw scores on a test. And it says it's approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. So I'm going to go ahead and write that down so I don't have to go back and read that again. So the distribution of x is going to be approximately normal with a mean of 17.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. So I'm going to take the distribution of x, multiply it by 4, and add 10 to it. So hopefully you're able to define the variable y, the scaled score here. And hopefully you're able to find the mean and standard deviation. So here you have the calculations for your mean and the calculations for your standard deviation. So let me get that to show up correctly. Here's your mean, and here is your standard deviation. And my computer is not responding. Sorry about that, guys. Now, that is the mean and standard deviation of your variable y. So I'm going to go ahead and summarize that. So it turns out we end up having a distribution of y. The distribution of y is going to have a particular shape, center, and spread. In fact, the distribution of y is going to be approximately normal with this center and this spread. Now part B, I'm going to ask you to use that distribution to find a probability. What is the probability that a randomly selected student has a scaled test score of at least 90? Okay, so if this is a multiple choice question, you are writing a probability statement, you are drawing a sketch, and you're doing this on your calculator. So the first things first, I want to write this as a probability statement. So probability statement, at least 90. I want to find the probability that this is going to be at least 90. Remember what at least 90 means. That means 90 or more. So the probability that y is greater than or equal to 90. I'm going to draw a sketch. So again, this is going to be normally distributed. So I draw a normal curve centered at 78.8. And so if I have a value of 78.8, then I know that this number is going to be greater than that. So I'm going to shade an area to the right of 90. And if I do that, I want to find this area here, this shaded area in the tail. I can do that on my calculator, and if I do that on my calculator, I'm going to end up getting a probability of 0.2306. But just for review, if you decided to show work, like on a free response or something like that, of course that means you're going to have to calculate z-score. You want to show some work. and get a number like this. If this is on a multiple choice question, the multiple choice question, they would have the same answer to 3 decimal places. So if it was multiple choice, one of the choices might be 0.230, for instance, and both answers would round to that. Okay, that's it. Hopefully you guys did what you were supposed to do. Don't forget to check your March Madness picks. I should have those posted on Blackboard as well. If you have any questions, come in after school. I will be around after school tomorrow, and also tomorrow meaning Friday, of course. And if you need to send me an email or something, you have a specific question, I can answer those as well. All right, have a great weekend, and I'll see you guys next week.